What specific problem does your proposed method, which combines the regularized RPGAN loss, aim to solve in the context of existing GAN architectures and their limitations?
The proposed method, which combines the regularized RPGAN loss, specifically aims to address two critical issues in existing GAN architectures: stability and mode collapse. Traditional GANs often suffer from instability during training, leading to non-convergence, particularly when the discriminator is not properly regularized. By incorporating zero-centered gradient penalties, R1 and R2, into the RPGAN framework, our approach enhances the stability of the training dynamics, ensuring that the generator and discriminator can converge effectively. This regularization not only mitigates the risk of mode dropping, but also allows for the use of modern backbone architectures without relying on empirical tricks, thus improving the overall performance and diversity of generated images. Ultimately, our method demonstrates that a well-behaved loss function can simplify GAN training while achieving competitive results against state-of-the-art models.
How does the proposed method or algorithm work? Illustrate the key steps of the methodology, particularly focusing on the modifications made to the relativistic pairing GAN loss and the integration of zero-centered gradient penalties.
The proposed method enhances the relativistic pairing GAN, RPGAN, by integrating zero-centered gradient penalties, 0GP, to improve stability and convergence. The key steps involve first augmenting the RPGAN loss with these gradient penalties, specifically R_1 and R_2, which penalize the gradient norms of the discriminator on both real and fake data. This dual regularization ensures that the discriminator does not overfit to real samples, thus preventing gradient explosion and promoting stable training dynamics. The methodology demonstrates that with the inclusion of these penalties, the modified RPGAN achieves local convergence, allowing for a well-behaved loss function that eliminates the need for empirical tricks previously used in GAN architectures. Ultimately, this leads to the development of a simplified GAN baseline, R3GAN, which leverages modern network architectures while maintaining competitive performance across various datasets.
Can you provide a simple, illustrative example that demonstrates how your proposed algorithm operates in practice, explaining each step clearly with the help of this example?
To illustrate how our proposed algorithm, R3GAN, operates in practice, consider the task of generating images of handwritten digits using the stack-temness dataset. First, we initialize the generator, G, and discriminator, D, with a modernized ResNet architecture, ensuring that both networks have approximately 25 million parameters. During training, we employ the regularized loss function that combines the relativistic pairing GAN loss, RPGAN, with zero-centered gradient penalties, R_1 and R_2. This step stabilizes the training dynamics, allowing G to generate diverse samples while D effectively critiques both real and fake samples, preventing mode collapse. As a result, we observe that our model achieves full mode coverage, recovering all 1,000 modes in the dataset, while also reducing the KL divergence between the generated and real distributions significantly, demonstrating the effectiveness of our approach.
What are the theoretical and practical benefits you encountered using your proposed method over the traditional GAN frameworks? How do you quantify these benefits in terms of performance metrics like FID?
The proposed method, which combines the regularized loss of the relativistic pairing GAN, RPGAN, with zero-centered gradient penalties, R1 and R2, offers both theoretical and practical benefits over traditional GAN frameworks. Theoretically, it ensures local convergence, addressing issues of non-convergence and mode collapse that plague traditional GANs, as demonstrated in Proposition 2. Practically, this approach allows for the removal of empirical tricks previously necessary for stability, enabling the use of modern backbone architectures that improve performance metrics. For instance, our simplified GAN baseline, config B, achieved an FID of 12.46, while the improved architecture, config E, reached an FID of 7.05, surpassing the performance of StyleGAN 2. This quantifiable improvement in FID indicates enhanced sample quality and diversity, showcasing the effectiveness of our method in generating high-quality images.
What experimental design did you utilize to validate or test your proposed method? Specifically, discuss the datasets used, the metrics implemented, and how these contribute to demonstrating the effectiveness of your approach.
To validate our proposed method, we conducted experiments using several datasets, including StackTemnist, FFHQ, CIFAR10, and ImageNet. We specifically measured the Frechet inception distance, FID, as a primary metric to evaluate the quality of generated images, with lower FID values indicating better performance. For instance, our R3 GAN model achieved an FID of 7.05 on the FFHQ 256 dataset, surpassing the performance of StyleGAN 2, which demonstrates the effectiveness of our approach. Additionally, we assessed mode coverage and KL divergence, particularly on StackTemnist, where our method achieved full mode coverage and significantly reduced KL divergence from 0.9270 to 0.0781. These metrics collectively illustrate that our method not only stabilizes training, but also enhances the diversity and quality of generated images compared to existing state-of-the-art models.
What limitations or drawbacks did you identify in your proposed method during your experiments, and how do you suggest addressing these limitations in future work?
In our experiments, we identified several limitations in the proposed R3 GAN method. Firstly, while our model demonstrates competitive FID scores, it lacks dedicated features for downstream applications such as image editing or controllable generation, as we removed functionalities like style injection from StyleGAN. Additionally, we did not incorporate advanced techniques such as adaptive normalization or multi-headed self-attention, which have been shown to improve FID significantly in previous literature. Furthermore, our evaluation of scalability was limited to lower resolution datasets, and we have yet to verify performance on higher resolution ImageNet data or large-scale text-to-image tasks. To address these limitations, future work should explore the integration of omitted features and techniques, as well as conduct comprehensive scalability tests on more complex datasets.